All right, so let's start with just sort of an introduction to the basic ideas with circuits. So fundamentally, what do we need to keep track of within circuits? Well, really there's two things. One of them is energy, and the way that we're going to tend to do this is to think of this in terms of the energy per charge or the potential difference or the voltage, right? So all those are really saying the same thing, and so keeping track of the energy per charge basically says whatever the charge carrier is within our circuit, we don't really care. We're just going to keep track of the energy per charge of those charge carriers in terms of the potential. Well, the other thing that we're going to keep track of is the charge carriers themselves, and we're going to keep track of them in terms of the current. So there will be situations where there will be no current flow. There will be situations where there will be a steady state current flow. There will be situations where we have a time varying current flow. And all that is really just keeping track of all that is really just a way of keeping track of how our charges move around the circuit. So for starters, just a basic definition, what is current? Well, the easiest way to think about it is that it's just the rate of flow of charge in a wire. So fundamentally, this isn't any different from the way that you might describe, say, the current on a river. That would just be the rate of flow of water down the river. Well, this is just the rate of flow of charge within the wire. Our definition for current is, again, it's basically the charge per time that flows past, right? So if we want a rate, well, this is a rate with respect to time. So the instantaneous current is given by dq dt. So just keeping track of how much charge goes by its rate in time. Obviously, if we have a constant current, then we can take these little d's and turn them into deltas, because basically that means that this value isn't changing for a constant current. So our rate is always the same, and so we can just think of it as well, take any chunk of time you want. It can be infinitesimally small, or it can be, it can be moderately large, and as long as you keep track of the charge flowing past over that chunk of time, that's still going to get you what the current is. In terms of units, well, units of charge are coulombs, units of time are seconds. So this is a coulomb per second is the unit of current, but that has its own definition. That's the ampere, and in fact, the ampere is really, in terms of the way that the SI unit system is set up, the ampere is one of the 7 fundamental units of which all others can be built. So the ampere is the unit for current. So how do you create a current within a wire? Well, basically what you do is we've talked about how if I have a conductor, right? So my wires, they're made of metals, they're conductors. In a static equilibrium situation, the surfaces are going to rearrange themselves on the surface of the conductor so that there's no electric field. Well, a static equilibrium situation tells me, electrostatic equilibrium says that there's no current. My charges aren't moving. This is the opposite of that. So this is a situation where the surface charges are going to create an electric field inside my conductor, which will then drive current. So here I have electric fields within my conductor, and then the current is really just the rate at which the electric field seems to push positive charges through the wire. And this is a critical distinction. So we know that fundamentally the charges that are really moving are electrons. We know that electrons are really negatively charged particles. Because we're keeping track of basically the energy per charge, it doesn't really matter. And so just by historical convention, and in fact you can blame Benjamin Franklin for this, he assumed that what was moving was positively charged. So he just set up the situation that said, current is driving positive charges in the direction of the current flow, and we just keep that convention. So the direction of the current is in the direction of the electric field, because we're effectively pretending that what we're driving with the current are positive charges. So here's a situation where, again, we set up this electric field, right? The surface charges on our conductor, on our wire, set up this electric field, and they seem to drive, that electric field seems to drive positive charges, in this case, in the same direction as the electric field. And that's the direction that we talk about the current flowing in. Right? Even though, again, we know that the electron current actually runs in the other direction. We're just sort of going to ignore that detail. So we said before that currents can vary in both space and in time. Varying in time, well, we've sort of already dealt with that, right? If it varies in time, then I can just take the derivative of the function of the charge, right? So if I know the charge is a function of time, take its derivative with respect to time, that'll give me the current. Varying in space basically says, well, what I can do is I can define this new quantity called the current density. And then the current density happens to be a vector. It happens to basically be the current per unit area. And so I can dot that in with some tiny little area elements across my wire, or whatever the current is flowing through, and then just do the double integral. So this looks an awful lot like the integral we've been doing for electric flux, and it works effectively the same way. Right? The total current is basically just add up the current density across all your little area elements. Now, the other way to think about the current density is it works out that it relates to the electric field in this way, so that the current density is equal to little lowercase sigma here is the conductivity. So this is just a property of your material, right? This is telling you something about how good of a conductor your material is, times the electric field. And so fundamentally, this is actually a really important equation. We won't use it all that often, but in terms of just giving us an idea of what's going on with our current, basically this equation tells us that electric fields produce currents. So the electric field on this side, and then how good the material is. So I've taken some conductor, I've set up an electric field inside that conductor, how large that electric field is, and then the amount, and then how well that conductor conducts electricity is going to basically tell me how much current I'm able to drive. So this is one way to think about Ohm's law. It's not the most common way that we'll think about Ohm's law, but this is simply one variation. Right? You can get from one to the other just by basically a little bit of algebra. So this is one way that we'll think about what's going on with Ohm's law. Units for current density, well, again, if it's current per area, then that's got to be amps per meter squared. So that's the units of current density. All right. So we've said we need to keep track of energy, we need to keep track of charge, we're going to keep track of energy in terms of voltage, we're going to keep track of charge in terms of current. How do we keep track of energy and charge? And the answer to that is there's two rules known as Kirchhoff's rules. The first one is the loop rule. And what the loop rule tells us is that the sum of the potential differences across all the elements around any closed loop must be zero. And so we'll write it this way mathematically, and it just says the sum of all the potential drops and increases as you go around some loop, some closed loop, has got to be zero. So what does that mean? Well, mostly it means start at any point you want to. Here I happen to be starting at this particular red dot. And then walk in any particular direction. And what has to happen, according to Kirchhoff's rule, is you have to, whatever your, in this case, as we're going from the negative terminal to the positive terminal of the battery, we would have a potential increase. Whatever that potential increase is, it basically has to be equal to the potential drop that we will experience across resistor 1 and then across resistor 3. So this will end up being an increase. These two will end up being drops, and we'll talk about, we'll talk in class about how to figure out whether you're looking at an increase or an increase of potential or a decrease of potential. But what Kirchhoff's loop rule says is just go around any closed loop, and all the increases plus all the decreases have got to add up to zero. You pick a different loop, great. Now I got an increase across this battery. It's got to be equal to the decrease across resistor 2 and the decrease across resistor 3. Pick a different loop that doesn't have a battery. So here I'm starting at this point, still going clockwise in my loop, and so whatever I drop, this would actually be a drop across R2, I've got to increase as I come this way across R1. So that one of these, when I'm walking in this direction, if I'm walking across, if my closed loop only sees 2 resistors, well, one of these has got to be an increase as I walk across it. The other one will be a decrease. And again, we'll talk about how to figure out when we're increasing across a resistor and when we're decreasing across a resistor. All right. Fundamentally, what the loop rule is telling us is simply that energy is conserved. Right? So when we walk around a loop and end up back where we started, it's basically saying that the energy that we picked up across all the potential increases, we had to lose across all the potential drops. So the loop rule is really just a statement of conservation of energy. Second rule is the junction rule. And that tells us that the sum of all the currents entering any junction must equal the sum of the currents leaving that junction. So again, mathematically, we're going to tend to write this as the current coming in equals the current coming out. And again, this has to be true for each junction. So for starters, what is a junction? Well, a junction or a node, those are synonymous words, are basically places where the current can go in multiple directions. So the current can either come this way toward resistor 1 or it can go on this way towards resistor 2. So to sort of use anthropomorphic terms, we'll say that basically here at this junction, current has a choice about which way it wants to go. It doesn't have a choice through here because there's no other way for it to go but just go forward along the wire. It gets to the junction, now it's got a choice. It can go this way or it can go that way. So there's going to be some current coming in from the battery. And then there's got to be some current going out, in this case, to our 2 resistors. And so all the junction rule says is the amount of current that comes in has got to be equal to the amount of current that goes out. You got a second junction down here. And so our junction rule has to apply. And again, it's fairly easy to see that whatever comes out of this junction across resistor 1 is going to come in to this bottom junction. Whatever comes out across the top junction, goes across resistor 2, is going to come into the bottom junction. And those 2 currents will recombine and go back out into the battery. And so what's effectively the I out at this bottom junction is exactly the same as the I in at the top one. Now, fundamentally, the fact that we can't lose any current in our junction is basically a way of saying that charge is conserved. So we have conservation of charge. We're not losing charges, we're not gaining charges. Whatever charge comes in, it's got to go out. That's sort of, again, fundamentally what our junction rule is telling us. So we've tried to set up an idea that says the 2 key things that we're going to keep track of within circuits are energy and charge. And fundamentally, our 2 Kirchhoff's rules are conservation of energy for the loop rule and conservation of charge for the junction rule. All right, the other detail that we're going to need to get good at quickly is how do we connect elements. And so here you'll notice, right, we've talked about the different types of circuit elements that we'll be connecting, right? So these could be capacitors, resistors, inductors. But for the moment, I don't care. I'm just going to call them element 1 and element 2. And so what I want to talk about are the 2 ways that I can combine these elements. The first way is what's known as in series. So my 2 elements are in series if all the current traveling through element 1 must travel through element 2. So basically you can take your finger and run it along the wire, and you got to go across element 1, you come out, there's another wire, there's no place else to go, you have to go across element 2, you come out of element 2. So these 2 elements are in series because there's simply no other option for where the current can flow. The other way we can connect things is in parallel. And so you'll notice that in parallel, current has a choice because there are junctions. Right? So here's a junction on this side, here's a junction on that side. So the current's going to come into this junction and split. Some of it will go across element 1, some of it will go across element 2. They'll come back into this other junction, they'll recombine, and they'll go out. So for circuit elements in parallel, the current that flows across element 1 can't flow across element 2 because that current split away and went through element 1 while different current split and went through element 2. So connecting elements in parallel requires a junction. Connecting elements in series means no junction. All right, and so these are the ways that we'll connect our elements. And so fundamentally when we're looking at circuits, we can always come back to pick two elements and try and figure out whether they are connected in series or in parallel. And that's how we'll sort of start to build up more and more complicated circuits.